let's get started. Good morning, everyone. It's my pleasure to be here today on the stage. And my name is Boris Trofimov. I'm from Sigma Software. And today, let me speak about nature and human body as an infinite source of inspiration and design ideas for us software engineers. What we can borrow from nature, what nature can teach us, or what nature can confirm that we are at least on the right way. So before we get to specific particular learnings, let me share a few, I would say, examples on beautiful connection between software in our minds and software we develop. The first example is protein synthesis inside our cells, which looks suspiciously very close to what is executing software application, which actually you do usually. And protein molecules, they are essential to our body, right? So they are building blocks for our cells, and cells produce them on a regular basis. So it's essential material. And I think that humans invented this architecture, consisting of three major blocks: CPU, RAM, random access memory, and hard drive. But looks like nature figured out the same. It's amazing how nature came to the same conclusion and came to the same breakdown. All three components exist when protein is being synthesized, and we'll take a look at them. All right, so I'm sure that everybody is familiar with DNA molecule. It's a biological code, and DNA is a blueprint. It's a blueprints, instructions to create different objects, for instance, to create that actually very protein. And nature had to invent how to deal with information on biological level. We live in materialized world. We don't live in informational world in certain sense. So we have to respect somehow, and nature have to respect somehow physical reality. And DNA is a response. So DNA contains those blueprints. Nature had to invent how to represent biological bit of information, right? So the least piece of information. And it is called, like, it actually has 4 values. Nature registered 4 values for the biological bit. And those values are called nucleotides. There are 4 values. Also, nature had to invent biological byte of information called codon. And codon is a 3 sequential nucleotides in a row. And as you can see that maximal cardinality of the codon is 64 values, and only 20 of them is reserved for particular amino acids, which is essential material for our protein, which we're going to build today. And what the rest of values, right? 44 values. They are reserved by nature for different purposes, and some of them will be revealed today. All right, so DNA molecule is our hard drive and quite sophisticated file system. You will see that if you ever faced before with parsing binary files, you might find some similarities with what nature actually doing when loading and reading those information from DNA. So DNA is molecule which is hard drive and file system. It consists of files. Literally, it has files called genes. And those files are a sequence of codons, and those codons are instructions to build different things. For instance, build our protein. And order here matters. Sequence of codons define the order in a protein molecule. As I told you, nature invented biological magic bytes. Just a few of them. Promoter. Promoter, it's a sequence which identifies the location of a file on a DNA. And there is stop codon, which identifies the location of the end of the program on a DNA. Pretty straightforward. And I'm sure that you know that DNA is actually double helix. So it has 2 strands. Major, called template, and another one called coding. And the interesting thing is that those strands are complementary to each other and anti-parallel. It means that if you corrupt one strand, it's possible to recover the first strand based on the second strand, because the bits locating on the same positions on 2 strands are complementary to each other. They have opposite values. That's a very, very interesting idea that nature came up to, and it looks like biological RAID array, at least very close to it. All right, so in order to execute something, you have to load something into a memory. Nature had to invent input-output processor called RNA polymerase. RNA polymerase, it knows which protein to build, and it uses that template, that only one strand which contains information, because that backup strand, it also contains information, but it is inversed, so we cannot use it directly for reading. So only template strand will be used by RNA polymerase to read information, to load our application into a memory. So what RNA polymerase does, it does quite simple work, at the same very complicated work. It finds corresponding promoter on a template strand. It melts DNA in that place, and it unravels strands from each other and creates a little tiny bubble between those strands. And it wraps it, and what it does, it actually moves from left to right on template strand, and it reads and copies codons one by one in the same order to the brand new object called mRNA. Probably you know it, mRNA. And this object, we can treat it as a flash drive. Just flash drive to transfer data from one location to the operational memory, in a certain sense, if you will. So RNA polymerase unzips, literally unzips helix in front of it, and zips again, like restores it in actually behind it. And it does the process till the moment when it finds the stop codon. It means that the flash drive should be finalized, and actually loading process is done. And on early stages, copying process quite vulnerable because of specificity of chemical reactions. And on early stages, this copying process might be aborted. And RNA polymerase, it just tries to do the same several times. So it just does several retries to read and make this connection stable enough to continue reading and copying data. I'm a big data engineer, so for me, like, my ETL jobs might fail time to time. It's a reality. They might fail because of different reasons, like transient errors, input-output errors, connection errors. And what we do, we just rerun them. Of course, in an automatical manner, but we rerun them. And good to know that nature didn't invent anything better. So rerun, and that's not too bad. Okay, so we have our application located in our flash drive, but we need to load it into our memory. Initially, mRNA was created in nucleus, but operating memory is cytoplasm, where all those amino acids, building blocks of protein, are floating around. So mRNA is transferred to cytoplasm, and then there is another component, another processor called ribosome, which is a Turing machine, if you will, and tape will be our mRNA, which is floating somewhere close to it. So ribosome, what actually ribosome is doing? It again, now we have binary file, we need to parse it. So ribosome parses it. It tries to find causal consensus sequence and start codon. In certain, again, like thankfully to chemical reactions, it tries to immediately find those sequences, our magic bytes on our mRNA, and start interpreting them. So now ribosome has to execute our application and build protein. And what it does, it, again, from left to right, it does it for every codon in a row. It takes corresponding amino acid coded by this specific codon, and this amino acid is transferred by another object called tRNA, but it doesn't matter for our discussion. And it just chains them one by one and creates a protein molecule in the same order. And once ribosome finds another magic byte called stop codon, it finalizes process. And protein is ready to be used by cell. Brilliant. And by the way, another thing here is that protein and mRNA, it's rather mRNA. mRNA can be reused by nature. Nature doesn't want to waste energy. So it uses a certain sort of caching. And this mRNA as a blueprint might be used several times to execute our program several times and build the same protein molecule if cells need several proteins. All right, ChatGPT. I think it would be totally disgraceful not to mention about ChatGPT. Deserves to have a separate slide, and there is a lot of hype nowadays about it. And behind this hype, there were countless attempts to simulate our brains, as you know. And for a long time, it looked like cargo cult. We tried to design our neural networks, and they didn't work, at least as we wanted. They worked somehow, but it wasn't breakthrough. And we did it for decades without dramatic success. And only after 2014, they invented generative adversarial networks and GPT transformers. They figured out what has to be changed inside architecture, what kind of indirect self-training should look like, right? And then breakthrough came and ChatGPT came to our lives. And I'm saying this for sake of honesty because we borrowed neural networks from nature. We made it work, and future is scaring a bit because of that. And I'm saying this because of another reason. It brings up quite interesting question: are we computable beings? Can we be replaced with huge, giant computer, so to speak, and therefore Turing machine? Computable here means that something is computable when it's possible to invent algorithm to exactly simulate the same behavior. And if we have algorithms, then we can build Turing machine, and then we can implement it on any programming language and so on. So are we computable beings? Our brain, as you know, is a huge, giant, designed biological neural network. It has about 90 billion neurons. And scientists have pretty good, at least they thought, pretty good mathematical models of neural networks. And most scientists think that they are pretty precise. Yes, there might be differences in architectures, in specific things, but models itself are more or less correct. And if so, then we have another statement that neural networks can be simulated by Turing machines. There is equivalence between Turing machines with finite tape and neural networks as a state machine. And if so, then it means that our brain and any logical reasoning that we have might be or is computable. You might say, and what? Well, there might be some far-going consequences depending on your beliefs. The most straightforward implication is that there is no big difference between us and those robots from Western world TV show from Netflix. Our behavior completely is determined. Another implication is that the universe has laws, and there is a famous Gödel theorem which sets hard limit on any system, any theory that can be described with symbols. Simply, it states that there are things, regardless of language, of approach, of logical reasoning, there are things in our universe, in our world, that cannot be fully described and fully proved by computable beings, by us, if we believe that we are computable. And that's quite a hard limitation. If you believe in Laplace demon, then probably things might get even worse because if you know location of all particles in the world, then you can predict the next state of the universe based on previous state. It looks quite scary, and most of scientists don't believe in Laplace demon. Because it's impossible, as we probably know, because of quantum mechanics law, to determine the location of all particles with certain precise and have some extra information based on that. Anyway, a lot of scientists don't like the idea that we might be computable. And among them is a famous Roger Penrose, is a brilliant mathematician and physicist, who is, by the way, a Nobel Prize winner. And they think that the key is somewhere in microbe world. There should be an explanation. There should be a key to explain why we're not computable. And they claim that, yeah, we have programs inside our brain. Brain is Turing machine. We have a tape somewhere located in our brains. But there is another tape, magical tape, located somewhere in the micro world and where new instructions might come. So they believe that, these scientists, that we are not closed system. And our brain has an interface to that micro world. And this interface is presented by tiny micro units, subunits called microtubules, they are located inside neurons. And distances are so small that these microtubules might register quantum effects on that level. And they behave as an observer in certain sense. And when like decision is not made yet, the universe like exists in several states at the same time. And once decision is made, there is a collapse of wave function, and there will be a quantum effect registered, and our microtubule would behave as an observer. It would register the signal, it would translate it to signal, and translate it as a signal, and we will think that decision is ours. It's just, of course, interpretation, but it's scientifically explained by Roger Penrose, who believes that we are not computable beings, and that's why we can do a lot of things and prove Gödel theorem and prove other things that computable beings probably cannot. That's a very interesting thing, and think about it, it's a very interesting thing. Worth some time to try to connect these dots. All right, enough speculations. Let's talk about actually our learnings. The first chapter is domain-driven design. Looks like nature invented domain-driven design as well. A human body is a distributed system. I think that everybody could agree with that. It has parts called organs, and they work separately at the same time, work to achieve the same common goal. And every organ, we don't need to like imagine this. Every organ clearly has unique structure, unique abstraction tiers inside those individual cells. Very, very huge internal world. And we might say that every organ has unique domain-driven, domain-specific language and bounded context. And every organ has also unique communication, unique commands, unique events, but communication channels are unified and the same. We will talk about them a bit later today. But thing is that organs can receive commands outside and send events somewhere outside for whom it might concern. And who it might concern? Brain. Brain behaves as a coordination center, which is pretty obvious, that sends those commands, receives those events. That's pretty similar, but doesn't look like it might be treated as a processor manager or Saga. Looks like. I think that it might be treated as Saga. And we have, by the way, beside the brain, we have spinal cord. And nature, some of Sagas, we can say that are deployed into spinal cord, and the reason is locality and latency. Our body has some modes like fight or flight, where body is collected and in the face of stress, it has to react quick. And this mode reaction should be pretty quick, right? And it should be we should act fast. And in order to do this, nature thought that probably we would like to put these coordination centers, Sagas, which will behave as state machines, closer to organs. So they're located like, we might treat, by the way, them as those lambda edges deployed on regional deployment things, instances. So very similar like that. And another implication is that almost no horizontal connections between organs. All communication comes through brains and spinal cord. That's important implication, by the way, and again proves that it looks like domain-driven design. By the way, spinal cord serves another function. It amplifies signals and works as an API gateway in certain sense. Like it would be naive to think that all organs connected to brain directly. No, nature is smart enough not to do this. So it uses API gateway, spinal cord, to transmit signals, to group them, clean them, amplify, and so on. All right, so lessons for us software engineers, what we can do. Well, clearly, in my opinion, domain-driven design is an essential part for backend engineers. And first lesson, introduce functional bounded contexts. And for every bounded context, clearly we need to introduce microservice or microservices if it makes sense. In most cases, it doesn't make sense to break down into several microservices, but there are cases. Do recursive breakdown. The way how we break down solution into bounded context might be applied to individual bounded context itself, right? So we can open hood of our bounded context and see that the same ideas might be found there. We might see aggregates, sagas on level, downstream level, right? So all the same ideas and decomposition can be applied on the level here. And actually there is like, fractal ladder somewhere downstairs. And I think that the most underestimated thing is domain events. Still not a lot of engineers still use domain events, but it's essential part. They can be and should be used to indicate that the change of aggregate and bounded context has been changed. For whom it might concern, right? It's broadcast objects. And when Eric Evans, who is the author of famous book and domain-driven design itself concept, was asked what he could add to his famous book, what was missed probably. He simply added that domain events. That's something that I didn't see from very beginning. So, yeah, domain events important. Adaptivity and energy efficiency. Our body has energy efficient mechanisms to regulate body temperature. For instance, when it's cold, then our blood vessels constrict and reduce blood flowing to the skin, and this minimizes heat losses, right? And vice versa, when it's hot, then wetting and that vessel dilation, what it does, it actually helps get rid of extra heat from body. It also is important, and it's pretty smart. There is efficient energy conservation mechanisms. Nature stores energy inside, in a form of glycogen, inside liver and muscles, and as body fat as well. And it helps when it's needed. It helps to mobilize it, right? To mobilize it, and it can be extracted. Energy can be extracted from the glycogen and ensure continuous energy supply when it's needed, when there are different modes like that, what I mentioned, called fight or flight. All right, so energy recycling. Do you remember that example with mRNA, which might be used several times? That's actually a great example of nature, that nature tries to do the best to recycle and reuse a lot of things if possible. And another example is prolonged starvation. In case of prolonged starvation, what body does? It breaks down non-essential tissues. Sorry? Yeah, I'm very sorry. Okay. I should stand on this pose only, looks like. So what it does, it breaks down those non-essential tissues into smaller components and recycles them and produce some energy because of that. Lessons for us. First of all, consider serverless. And clearly, like kind of auto-scaling, actually it's automatic resource allocation. Auto-scaling is just a bonus because of that. It might be trivial, but for a long time, I mentioned that I'm a big data engineer. For a long time, for me, it was like a regular way and only one way to build clusters. We built them living for months. They were like long living objects. We spent a lot of efforts trying to make them live and keep them alive. We spread our jobs there. They've been running. And if cluster is down, everything like the world is collapsed. It was a disaster. And to be honest, it was quite dangerous. And like serverless is I wouldn't say silver bullet, but now we can solve a lot of problems with the serverless. And for instance, on big data, we use serverless on all tiers. We use serverless on computational layer, like we can create clusters on demand and easily utilize them and recycle once task is done. And it's much easier for us rather than, again, try to treat it, keep it, love it, and so on. Better to create and destroy after it's not in use anymore. Automatic resource allocation, it helps to reduce costs in certain sense, and it helps to tolerate some spikes in loading, something like that. And get to back to my example, serverless helps not only in a computational tier, we also started using serverless on a storage tier. It was insane, to be honest, to accept it, that even possible to have databases with a serverless technology, but they exist. Like just an example, Snowflake, it's a brilliant example. There are other examples, so it's possible. And data governance, so on all tiers you can use serverless technologies on backend as well, on backend world. It gives a great balance for us, for engineers, between costs, our comfort. Now we can focus on more pleasant things. We can focus on evolving solution rather than trying to keep it alive and put all efforts, maintenance efforts, to make it live. Pretty straightforward advice: data compression and conservation. Probably the only thing is, don't forget about if you have some data and you cannot drop it, but you need it. Don't forget that there are Glacier, if in terms of S3, AWS, and you can put data to Glacier and reduce costs and not lose your data. It's like, again, it's a underestimated solution as well. Always measure cost of change. It's important, in my opinion, for every new feature you're going to deliver, important to measure the bill increase, what will be bill increase, what it will look like after your deployment. And on my project, we use a cup of coffee metaphor. So it's like idea of story points. We like $5 or so. It's like, oh, sorry. So we translate our bill increase into cups of coffee. How many cups of coffee it will cost to us? Like, all right, so this new TL job will cost 1 cup of coffee per week or 4 cups of coffee per month. And we strive to minimize amount of cups of coffee at the end of the month. That's our goal. It's easier to accept it. Still, money is the same, just metaphor. And of course, monitor and know your daily bill. It's extremely important. Every time when you take a monthly bill, it's like a brain teaser. It's very hard to understand why it was increased. And if you do it on a regular basis, it's pretty straightforward. All right, so fault tolerance. Our body is designed to work for years. And at the end of the day, it looks like we are biggest enemy to our body. We have organs which are designed to work in very heavy conditions and under very conditions. You all know them, like heart, liver, stomach, right? They have a lot of protection mechanisms. And like, for instance, partition tolerance or self-healing or retries, a lot of things nature invented to keep them high available. Another example, organ redundancy. Again, you know those organs: lungs, kidneys. Again, good design idea by nature to, I would say, mitigate spikes in processing, in loading in certain sense, or it might happen that, I don't know, one instance is down. So again, nature took care about these cases as well. Information redundancy. By this I mean that DNA, which is copied across all cells, and it's also was intentional decision made by nature. And yeah, there might be implications, but in general, it looks great. Self-healing, we have outstanding possibilities of self-healing, like those wound healing and all those immune responses when body is able to develop immune response towards unknown viruses and develop antibodies. That's also amazing things that we have. And efficient feedback loops. Our body monitors everything. And it might be like body temperature, blood pressure, blood sugar control, a lot of things. And all of them are monitored by nature. Nature does the best trying to keep us alive. Actually, available means we are alive and conscious. And lessons for us. Multiple availability zones. Yeah, I did it. Definitely worth considering these availability zones and load balancing. I think that it should be intentional decision. Yes, with serverless technologies and cloud technologies, you can enable them pretty quickly, but at the end of the day, you need to understand, do you need these availability options? It's so easy to over-engineer your solution, and we should be responsible. But if you need availability and requirements from customer, worth considering them for sure. Data redundancy, if we agree that we would like to introduce multiple bounded contexts, then the implication is that every bounded context has to have own database storage, database organization, and it should be separated as isolated storages, ideally. And don't be afraid of data replication. For instance, if you need information from another bounded context, yes, you can call it directly, like make an API call to another web service, a microservice, but that's a problem. If it's another bounded context, better not to do it. And there are ways how to avoid it. You can listen to events from that bounded context. You can replicate data from there or sub-data from it. It's also fine. It's a good trade-off. Most of projects indeed don't need availability. In most cases, you can just introduce smart monitoring, measure everything, collect information, build simple alarms, and it will be more than enough for you to react, to respond without those extra costs on availability. All right, CAP theorem. Interesting. By the way, are you familiar with CAP theorem? Could you please raise your hands? Okay. Not all of them, but okay. So in a nutshell, let me briefly tell you what CAP theorem is. So for any distributed informational store system, it's impossible for the system to reach three qualities at the same time: availability, consistency, and partition tolerance, regardless of decisions you can make. It's impossible to achieve all three qualities simultaneously. Some will be sacrificed. Like you can achieve consistency and availability, and partition tolerance will be sacrificed. And that's like hard limit on decisions we can make. And our body can be considered as a distributed informational store system. If so, then looks like it can be applicable to us. So let's play a game. I would just run through several options, and you would raise your hand to support that option. For instance, likely that nature has made some choice, right? We need just to figure out what it is. So what if nature chooses, and quick thing that I will share my guess right after the game. What if nature chooses consistency and availability over partition tolerance? Who likes this idea? Okay. What if nature chooses consistency and partition tolerance over overall availability? No hands? Maybe you have your options. Nope. No guesses? Only, you can choose any options. I would think of two, any two. You think that's the most applicable. And the third one actually should be sacrificed, right? So what do you think? Consistency and availability? Yep, please. Okay. Consistency and partition tolerance over availability. And availability, partition tolerance over consistency. Oh, I think that it's a spoiler. We're on the same page. Actually, let's break it down one by one. I think the same. Availability here means that it's a ability to be conscious and live, and looks like nature does the best trying to let us be conscious and live at the same time. So availability, all those examples with high availability organs and those protection mechanisms. So clearly our organs are designed to be available and let us be available. All latency limitations on oxygen delivery, right? We have about 30 seconds to deliver oxygen to our cells, and nature does the best trying to fulfill this requirement. Otherwise, cells would just simply die. strong feedback system. Everybody knows we have pretty good monitoring. Okay, so partition tolerance. Examples. I think that everybody could agree that it's possible to live with certain organ or peripheral disabilities. At least nature thought about it, right? And every cell has own unique copy of DNA, and it is possible to regenerate it and recreate proteins and other objects based on dedicated copy. So it is partition tolerant. What about consistency? That's a tricky beastie. So clearly that DNA copies might be corrupted. And there are all those diseases based on that, unfortunately. That's a reality. And signals can be lost. Actually, they will be transmitted eventually between brain and organs, but there are cases when the signals might be lost in the middle. And looks like nature likes eventual consistency. So yes, I think that it is availability and partition tolerance over consistency. So we are on the same page. All right, so let's move on. Nature thought that probably it would be a good idea to have some transport communication channels. Here are three major ones, and there is fourth one, but it's less romantic. So let's start with nervous system. It's a quite sophisticated thing, as everybody knows. It controls all life processes like blood pressure, temperature, fight or flight mode when you have to be collected, and it's essential. It changes a lot of processes inside our body. It implements communication between brain and spinal cord. And looks like the major types of signals are commands from brain to organs and events from organs to brain. Also, body separates concerns. There are isolated systems, nervous systems inside our body. For instance, system controlling muscles doesn't have any connection with system that controls organs. Again, with the idea that if something gets bad with one system, another at least can survive. That's, again, decision made by nature. And locality matters. That communication between organs and spinal cord in case of fight or flight mode. Low latency, the speed of signal is about 100 meters per second inside the nervous system. Length of all nerve fibers is about 75 kilometers. Another system called circulatory system. Circulatory system, it delivers oxygen, sugars, hormones, different amino acids, again, building blocks for our proteins, which are building blocks for our cells. I can call them as data messages. And circulatory system is a result of the fact that not everything can be built with just the signals, right? We are mechanical systems in certain sense. And nature had to invent a unified way to deliver some chemical things, like molecules, to our bodies. And this is a type of contract like for whom it might concern. But it's not event, it's rather a data message. So nature invented a unified way to deliver this kind of data to cells. And it has a pump, actually a heart, everybody knows it. And the reason, because we have a very limited time to deliver these chemical things to our cells. It's just about 30 seconds of round trip to deliver those objects to our cells. And heart does the best trying to avoid to meet this constraint, regardless of mode. Are we running, swimming, or sleeping? Neural network tries to the best. If needed, it can reduce length of those circulatory vessels by sending specific hormones, right? And then it is able to just make those circle short and trying again to meet condition 30 seconds. Total length of blood vessels here is 100,000 kilometers. It's insane. And last, but not least, lymphatic system. Lymphatic system, it actually serves two functions. The one is, it's a part of immune system. In our bodies, there are located tiny biolaboratories biolaboratories, and these laboratories, they receive a little portions of unknown viruses and try to actually build immune response, try to build antibodies against these viruses. It's one function. And the second function is that it serves as canalization. Cells can get rid of rubbish, and as this is a rubbish, it's a garbage collection, then nature thought, okay, looks like we don't need to invent, we don't have SLA, probably we can avoid using something like pumping here. And indeed, this system doesn't have own pump. So it has least SLA priority. All right, so lessons for us. Clearly, message-driven systems and design is attractive. Yes, in certain sense, it might be complicated, but looks like nature proves it's extensible and scalable. Maybe there is just a lack of frameworks, I don't know, but definitely it worth addressing. Back pressure enabled by design, for sure. We have to somehow distinguish commands and events, and we have to distinguish data messages as well. That's why we have RabbitMQ, Kafka, and other different channels. All right, ladder of abstractions. Last thing. So yeah, our body is a great example of ladder abstractions. We are functioning on multiple tiers, right? So we are, as an entity body, we operate on one level. We consist of different organs and systems. It's the downstream tier. If you open hood of this tier, it consists of other objects, cells. Cells consist of molecules, and so on. So every tier like that, it has unique responsibility, unique building blocks coming from downstream tier. It has certain, I would say, language. So it's completely different world in certain sense. And clearly our body is example that it's possible to break down complexity across these tiers. We are live example that it's feasible as a type of thing. It means that probably we should pay attention, more attention to abstractions. We introduce tiers, they reside, contracts, abstractions have gates between these tiers. Clearly, we need to define architectural levels through abstraction tiers, but not vice versa. So nature proves that it's possible. It's possible. All right, so my message to you, look around and learn from nature. Not just human bodies, the whole nature might be source of inspiration. And this inspiration was polished by million years of evolution. Thank you very much.